Okay, so here we're going to start with and define what is a matrix inverse here and why do we care about a matrix inverse, right? And what does that have to do with systems of linear equations, which we'll see immediately why this is going to be helpful, right? Again, if we're able to calculate it, I'll determine that it has an inverse. Okay, so here when we are doing scalar multiplication or just ordinary arithmetic, right, we're able to get to multiply by right some value, right? If let's say our number is 2, I know that if I multiply by 1 over 2, multiply that, I call it the reciprocal. Really, it's its inverse, right? It's multiplicative inverse because when you multiply, you get 1. All right, now what would that look like for matrices, right? Well, we've already seen that we have defined this idea of an identity matrix, right? And we're going to treat that as our 1 for matrices, right? So what if I was able to find, given some matrix A, I was able to find a matrix B that I get this, right? So essentially it undoes whatever A does. Right now, why would that be useful here, right? And again, here it would have to be, as we'll see, both sides here. All right, now why would that be useful? Well, if we think to our vector equation formulated in this way, here, well, if this matrix B existed, right, this would give me the identity, and then in time x, the vector x, you would just get the vector x, and then you would get this product here. All right, now if we think of how powerful that would be, right, we spend a lot of time talking about solving these systems of equations, right, doing reduced row echelon form. Well, this kind of bypasses all of that. All right, it just says, well, what if I just find this matrix B here that I've defined to be this right here, right? Uh, and then I solve my system, right, by essentially just working with matrices, right? Seems like a very powerful kind of tool here. All right, well, let's first define formally what a matrix inverse is. So MI matrix inverse. All right, so a matrix inverse is a square matrix. So again, only with dealing with square matrices. A square matrix A of size n is invertible or has an inverse, I should say, if there exists a matrix B such that AB is equal to BA, which is equal to IN. All right, so all of these are n by n matrices, right? And if this matrix does exist, we call the matrix B A inverse of A. All right, or A inverse, I should say. All right, so both products must be defined and equal the identity matrix. For now, we'll say we have to confirm both of them. Later, we'll look at a theorem that says if you do one side, that would be enough. But for now, to be rigorous, we'd have to confirm both sides here. All right, so let's do an example here. Okay. All right, so let's say that A is equal to the matrix 1, 0, 1. Okay, and 1, 1, 0, 1, 2. All right, and then A, or call it B for now. B is the matrix 0, 1, negative 1, 2, negative 2, 1, and negative 1, 1, 0. And I want to confirm or determine whether B is an inverse of A. All right, so we'll look at the products here. This is 0, 1, negative 1, negative 2, 1. Okay. All right. So here we could see by now multiplying this out, we get first row, first column, so 0, 0, hold on a second, 0, 1, negative 1, 2, negative 1. Okay, I'm double checking that I wrote this example down right. Okay, I did not write that down right. Give me 1 minute here. Okay, so here, let me redo that example here. So let's see, 1, 1, 1, 1, 1, 2, 1, 2, 3. Okay, so here, let's retry that again here. Okay. Okay, so matrix A will have to be 1, 1, 1, 1, 1, 2, and 1, 2, 3. Okay. And our B inverse matrix candidate to be 1, 1, negative 1, and 1, negative 2, 1, negative 1, 1, 0. Okay, and now let's confirm these products here. So AB, product 1, 1, 1, 1, 1, 2, 1, 2, 3, times the product 1, 1, negative 1, 1, negative 2, 1, negative 1, 1, 0. Okay, so again, going row by column. So that first row, first column, we get 1 times 1, times 1 times 1. And yeah, so that's 2. And then minus 1 gives me 1. Okay, now moving on to the second row. First column, so we get 1 times 1 plus 1 times 1 is a positive 2. And then minus 2 gives me 0. All right, moving on to the third row, first column still. 1 times 1, that's 1. 2 times 1 is positive 2, so we get 3. And then a minus 3 for 0. All right, and now move on to the second column, still now back to the first row. And we get 1 times 1, minus 2, so negative 1, and then plus 1, 0. Okay, and now second row, second column, 1 here, plus 1, minus 2, excuse me. Okay, so that is negative 1, and then minus 2 is minus 1, plus 2 back at 1. And then lastly here, 1, 2, 3, so we get 1, minus 4 is minus 3, and then minus 3, 0. All right, and now lastly here, we could see 1, we'll get 0. So negative 1 plus 1 is 0, last one is 0. Second row, we get minus 1, plus 1, 0, and then 2 times 0, 0. And then lastly, at the last row here, we get negative 1, plus 2, and then 3 times 0 is 0, so we get 1. All right, but again, all right, not quite done here. Okay, so let's flip these around and just confirm. So here we get 1, 1, negative 1, 1, negative 2, 1, and negative 1, 1, 0. And the other matrix is 1, 1, 1, 1, 1, 2, 1, 2, 3. Okay, and here we see doing the first row, so we get 1 times 1, that's 2, minus 1, get 1. All right, and moving along here, so we get 1, minus 2 is negative 1, plus 1 is 0. Okay, and then here we see again, and I'm moving a little quicker here, negative 1, 0, 0. Now moving on, we get 1, 2, minus 2, 0, and then 1, minus 2 is a negative 1, plus 2, 1. All right, and I think here, 0, 0, 0, 1. Okay, just doing a quick check here. 0. Okay, all right, so that looks all good here. So now we could say that since both of these products are I3, right, we could say that B is indeed the inverse of A. Right, or in other words, B is equal to A inverse. All right, and now what this kind of leads us to just kind of a bigger kind of a result here. So A here, given this vector equation here, right, now if I left multiply here, this is my identity, and then this is the product A inverse B, right? And this identity times the x vector gives me the x vector. And what this tells me here is that now I can solve really any vector equation for vector B, right? I can find a solution now very quickly, right? Actually, I could just switch out the B's as long as I did the calculation correctly for the A inverse, and I can solve a lot of systems of equations just by using this this product here. All right, next we'll learn how to find an inverse.